I'd like to thank the organizers for giving me the opportunity of the talk in this wonderful workshop, and also thank you for watching this movie. This talk is based on the collaboration with Yoshio Kikukawa and Hoiki Ryu in the University of Tokyo and Toshifumi Nomi in Kobe University. The topic of this talk is to investigate the similarity and difference between anti-de partition functions and de cosmological wave functions, and to ask the following question. Are these two quantities really related via analytic continuation? In this talk, I will consider equal time de correlators at late time. A main motivation is the application to correlators of inflationary fluctuations that we expect to play a role of a window for novel high-energy physics. In the following, we call the inserted fields phi bars the boundary fields because they are put near the future boundary of de spacetime in Poincare patch. Also, we introduce tau star as a regulator in the neighborhood of the boundary. Tau equals 0. Okay, I start with reviewing how these bulk correlators can be computed. So far, two methods have been known. One method is the so-called in-informalism that is based on the canonical quantization in the interaction picture, and the vacuum to define the vacuum expectation value is defined at the past infinity. In this talk, this vacuum is chosen to be the so-called Bunch-Davis vacuum. The other method is to use the wave function at the time when the boundary fields are inserted. That was, I think, first introduced by Maldacena in 2002 in the famous paper of the non-Gaussianity. This talk will focus on this wave function method. As usual, in quantum mechanics, the wave function can be defined as the path integral with the Dirichlet boundary condition with given boundary fields and the Bunch-Davis condition at the past infinity. In the semi-classical limit, this path integral becomes the exponentiated action at the classical solution that satisfies these boundary conditions. These boundary conditions mean the Dirichlet boundary condition and the Bunch-Davis condition. Then a bulk correlator is defined as the expectation value with the probability distribution defined by the wave function squared, as usual in quantum mechanics. Okay, let's move on to the comparison between the de Sitter wave function and the anti-de Sitter partition function. In the following, I will work with the Poincare patch of these spacetimes. The anti-de Sitter partition function is defined as the path integral of the exponentiated action under the Dirichlet boundary conditions, and its semi-classical limit is again the exponentiated on-shell action. Clearly, these two quantities, namely the Alias partition function and de Sitter wave function, have a parallel structure by definition. So it is often expected that the de Sitter wave function may be obtained by analytic continuation of the anti-de Sitter partition function in the semi-classical limit. So now a goal of this talk is to show that this is true if the mass of the field is light, but this correspondence is not true if the mass is heavy enough. To demonstrate this, we consider a theory of a free scalar of mass m. First, we need to solve the classical equation of motion under these boundary conditions, the Dirichlet condition and the Bunch-Davis conditions. The solution can be written as the product of the boundary field phi bar and the so-called bulk-to-boundary propagator B that is normalized such that the boundary conditions are satisfied automatically. In both cases, the propagator is a ratio of Bessel functions with the mass index nu. In ADS case, the bulk-to-boundary propagator is a ratio of Bessel k function. On the other hand, in Dosita case, the propagator is a ratio of the Bessel h functions. And the ADS case, the mass index is always real and positive definite. On the other hand, in Dosita case, the mass index is real if the mass is smaller than d half, but the mass index nu becomes pure imaginary if the mass is bigger than d half. This difference becomes important later. As we can see by comparing these expressions, especially the equations of motion and the mass indexes, the ADS side and Dosita side are related by this analytic continuation that relates the radial and time coordinates by z equal I tau, and the two masses, mass ADS squared is minus mass Dosita squared. So next, to compute the on-shell action, we use the elementary fact that the action at the classical solution is nothing but the surface term that comes from the variation with respect to the field phi. Then we find that in each case, the on-shell action becomes proportional to the Euler derivative of the propagator. Here, Euler derivative is defined here. Euler derivative theta x is x times the differentiation d over dx. Again, we can see that these two quantities have the parallel structure as long as the regulator z star or tau star is kept arbitrary. But by definition, the regulators must be near zero, namely infinitesimal. So we need to evaluate the derivatives of the propagators b by expanding them in the regulators. For this, we use these series expansions of Bessel functions that enter the propagators b. It is useful to note that the expansion of each Bessel function is the sum of two infinite series. One starts with the power that is minus the mass index nu, and the other series starts with the power, the mass index nu itself. Okay, before moving on to the detailed analysis, we must note again that in ADS case, the mass index nu is always real positive. But in Dosita case, the mass index nu can be pure imaginary if the mass is bigger than d half. This fact will turn out to be crucial later. Okay, let us first analyze the ADS partition function. As I mentioned before, the Bessel function is the sum of two infinite series. So we find that the derivative of b has a numerator that is the sum of the analytic term in momentum k that is proportional to d half minus nu, and the non-analytic term in k that is proportional to kz star to the power of 2 nu. Also, the mass index nu is positive definite now. So the power factor kz star to the power of 2 nu becomes of higher order. So we are free to expand the denominator in this power factor. As a result, we find this ADS partition function. Namely, this is the sum of analytic part that is d half minus nu plus blah blah blah, higher orders, and the non-analytic term, that is proportional to kz star to the power of 2 nu. Also, in ADS case, it's been well known that the analytic part is removable by adding a local boundary action. That is so-called the local counter term to renormalize the Baroque action. So the net result is the renormalized partition function contains only the non-analytic term kz star to the power of 2 nu. Okay, next let's see the case with a light scalar field in zeta space. In this case, the mass is taken to be smaller than d half. So the mass index nu is still positive. So the argument in the ADS partition function case still applies here. So the derivative of the Baroque boundary propagator B has the same structure as in the ADS case. Namely, the Euler derivative of B is the sum of the analytic part d half minus nu blah blah blah, and the non-analytic part that is proportional to minus k tau star to the power of 2 nu. Now to compute the Baroque correlators, we need the wave function squared, not the wave function itself. So we then find that the wave function squared involves the imaginary part of the Euler derivative of the Baroque boundary propagator B. So we find that this operation of taking the imaginary part eliminates the analytic part d half minus mu because it is a real number. So the wave function squared has only the non-analytic term, as in the ADS case. Again, namely, this operation of taking imaginary part plays the same role as adding the local counter term in the ADS case. Okay, once we find the wave function squared in this way, we can compute the two-point function. And this is consistent with the result based on the canonical quantization, so-called informalism. Okay, let's move on to the case with a heavy scalar field of mass greater than d half. In this case, the mass index becomes pure imaginary. So let's write the mass index as I mu. Here, mu is the square root of m squared minus d squared over 4. The starting point, namely the wave function, has the same form as in the previous cases. So one may expect that its expansion form via the series expansion of Bessel functions will be the same as the previous cases. But we can see that it has a big difference. Namely, the power factor of minus k tau star is now a phase factor because its power is 2I mu, pure imaginary number. So this power factor has absolute value 1. So it is no longer of higher order compared with the analytic part. As a result, we are not allowed to pick up any term out of the expansion of the denominator in the power factor minus k tau star to the power of 2I mu. So what we can ignore here is only the terms that are represented by the 3 dots. Furthermore, the wave function squared contains the imaginary part as in the previous cases. And it gives another difference because the analytic part d half minus I mu contains the imaginary factor. Therefore, the exponent of the wave function squared consists of not only the contribution from the non-analytic part with the dump factor exponential minus 2 pi mu, but also the contribution from the analytic part. This exponential factor, exponential minus 2 pi mu, or exponential minus pi mu in the denominator, that survives the imaginary operation, is a characteristic feature in the heavy mass case. Okay. Once we find the wave function squared in this way, we can again compute the two-point function, and the result is consistent with the result based on the canonical quantization. In summary, when the mass is lighter than the half, the dou wave function is the analytic continuation of the ADS partition function as expected, but when the mass is heavier, it is no longer true. Okay, this result can also be interpreted in terms of the holographic dual two-point functions. In Alias CFT, the dictionary is to identify the coefficient of the quadratic term in the exponent with the two-point function of a primary operator of dimension d half plus nu. Here we use the fact that the two-point function of an operator of dimension d half plus nu is proportional to k to the power of 2 nu, where k is the Fourier momentum. Normally, the same dictionary is applied to the dou wave function squared. But according to the result we obtained, we can easily see that dictionary is valid when the mass is lighter than d half. But when the mass is heavier than d half, the dual two-point function must enter the denominator in the exponent of the wave function squared. So the exponent must be regarded as the sum of infinitely many two-point functions that include two-point functions of the primary operator of dimension d half plus I mu, and also its shadow operator that has a dimension d half minus I mu, also infinitely many primary operators that have dimensions d half plus I mu times integer n. Finally, I'd like to give a brief comment on the case with interactions. When interactions are taken into account, the semi-classical partition function in anti-dou space and the wave function in dou space contain higher order terms in boundary fields in their exponents. And each coefficient of the power of boundary fields, that is represented by Vn, can be expressed in Witten diagrams. The structure of each Witten diagram is the same on the anti-dou and dou sides. So the difference comes just from the concrete forms of the bulk to boundary propagators that was introduced before, and also the bulk to bulk propagators that are building blocks of the Witten diagrams. Because the detailed forms of these propagators depend on whether the mass index nu is a real number or a pure imaginary number. Okay, let me summarize the talk. We demonstrated that when the mass is lighter than d half, the ADS partition function and dou wave function are related by analytic continuation. But when the mass is heavier than d half, such analytic continuation does not apply anymore due to the oscillatory nature of the momentum power factors. The essential reason of this difference is that the mass index nu becomes a pure imaginary number when the mass is bigger than d half. This result holds whether interactions break part of dou conformal symmetry or not. So This result can be applied to, for example, models of inflationary fluctuations with, for example, linear mixings or derivative couplings of scalar fields. We computed such cases and investigated their analytic structures. One of the open problems that follows naturally is to extend such analysis to the case with spinning fields. Okay, thank you very much for your attention.